Recording. Okay, good. So let's see. Let's see if it doesn't crash. Let me just double check. Okay, we should be recording now. So welcome to the 8th lecture. Excuse me, 8th lecture on NLP with deep learning. And today we're moving to something very substantial. So we're going to be talking about a very important architecture that everybody is familiar with, and if you know how it works, so today you will know how it works, and it's one of those transformer models. So who has heard about transformers? That's great, pretty much everybody. Who hasn't heard about transformers, this is a place you will learn about transformers. And one of the very famous architecture or models is the BERT model. So if I'm going to talk about BERT, I don't mean an animal like BERT, but the BERT. If you do auto captioning on YouTube from these lectures, it will always say like BERT as an animal. Well, anyway. It's BERT. Okay, so let's start with some motivation, and let's start with a thing which is somehow a prerequisite to understanding why these things work, and it's this multitask learning or transfer learning. So multitask learning has been here from the 1990s already, and this is from the paper from Rage Caruana. And the thing is that you might have a neural network here. There are some inputs, some inputs here, some hidden layers, and there are multiple tasks here which are actually trained on the same network. So you might have the underlying structure of the network is the same, and you might have different outputs of the network for different tasks. And these tasks could be somehow similar, these tasks could be different. And the idea is that by learning these tasks in parallel, we do better transfer to other tasks. So it should improve generalization. So theoretically, I mean, is it possible to change part of a network and train the rest of the parameters? Yes, of course. I mean, you just substitute one of the outputs in your computational graph with some other outputs for which you might have labels, and just train on. So you can start training on movie reviews and then start training on, I don't know, something else, some other text classification, and the shared representation in your network will be useful for both tasks. Okay? Conceptually, does it make sense? One example in NLP, for example, here is that, so this is from Anders Sogard and Jav Goldberg, one of the early examples of multitask learning, where they have basically, the main task was something with syntax chunking and super tagging, so some linguistic annotation of the sentence. And they also have part of speech tagging data, which part of speech is basically, what is part of speech tagging? What is it part of speech saying? What is part of speech tagging? What is part of speech? Yes?
He was talking about taking each word from a sentence and playing it for maybe an entity or even what kind of word it is.
What kind of word it is, you're close enough. So adjectives, nouns, and so these are part of speech. And part of speech tagging means every word is one of those. And the syntax chunking or the super tagging is a task which is somehow like more abstract, or in the hierarchy is more general, or more, I mean, I would say maybe more complex. So the idea is that these main tasks should basically benefit from part of speech tagging if the network already learned something about part of speech tagging. And that's what they actually observed. They said, like, if there's a hierarchy between different tasks, we show that it's worthwhile to incorporate this knowledge into the multitask learning architecture's design by making lower level tasks affect the lower levels of the representation. So here's a neural network, like some easy depiction. And when you go from down, the lower layers of the network are trained on this task, which is somehow simple and you have a lot of data for, so part of speech tagging. And then you might switch to other tasks like the main task, syntactic chunking. So here you're training the network to perform two tasks at the same time, and the different parts are shared then for the other task. So you're basically giving more, I don't know, information to the network, like more capabilities, learning something new, which can generalize to other tasks. It doesn't work well, it doesn't work all the time, but sometimes it's really helpful. And it's also, again, transfer learning. You learn on one task, and then you use the pre-trained weights to learn on some other task. Okay? Does it make sense? Cool. This will be very important, why everything works. Because you can learn, so we had something like that. I mean, we had word embeddings, right? We have word embeddings, which is in a way learned representation of words on some task. What was the task of word embeddings? Well, basically predicting whether, continuous back of words was like, is it the correct context or not? Or is it like the fake word or the right word? So task was kind of like superficial. But it learned word embeddings, it learned vectors, vector representation for each word, and then we can use it for like plugging into bigger networks to do sentiment analysis maybe. So here the idea was that they tried to learn a sentence representation, not just word representation, but sentence representation on a task, and then plug it onto the pre-trained representation of the network, which can generate representation of the sentence, plug it to other tasks. So the idea is simple, very same as we had in the previous slides. So what I have is, for example, natural language inference corpus, and they train LSTM network. So LSTM is the recurrent neural network, which we are discussing in the last lecture. So they train the network, and do you remember natural language inference, lecture 1? What is it? Was it about? NLI. So you have two sentences, hypothesis and text, and you try to predict whether, given the hypothesis, the text is entitlement, contradiction, or neutral. And there's 500,000 data points for that from this SNLI corpus. Okay, so you have data, and they try to pre-train LSTM to do this. But then it also learns, because LSTM learns at the last hidden state, it learns the whole representation of the sentence. So it learns the representation of the sentence. So it's like sentence encoder in a way. You take a sentence and encode it in a vector, and they use this pre-trained network to train it on other tasks later on. For example, so these tasks are Microsoft Research Paraphrase Corpus. I don't know the details, but I guess it's to decide whether one sentence is a paraphrase of another sentence. I guess this is the binary task. And the COCO data set, I actually forgot what a COCO is. Caption image retrieval. So something also with image things. The idea here is that if you don't pre-train your network on this task, you can train on the two tasks, on the COCO and Microsoft Paraphrase Corpus, and get some results. If you use pre-trained network on some other task, you get much better accuracy here, because the network has already learned something about maybe relation between sentences. So you pre-train your network on some task, and you can train it further on the other task, and it will give you, better scores. Okay? Any questions? Does it make sense, like conceptually, training on one task and trying on another one? Sounds simple. Well, it could be actually simple or not. It really depends. But anyway, so this is the motivational or the backbone idea. Like you train on something and use the pre-trained network on something else, and it should give you a lot of gain. The question here is, okay, so not a question. There is no question. We will come to the question later. But we were talking in the last lecture about the recurrent neural network. So we had an LSTM example, long short-term memory network. And what are the bottlenecks of these RNNs? If you remember, the RNN is... Sorry, you have a question? No. Yes.
So for the previous slide,
yes.
So the sentence representation is always like the output of one neural network, but it's the same for every box there.
I don't understand what you mean. Try say again.
So we have this dense sentence representation in every box, and this dense sentence representation can be the output of one neural network in each box, because we are that's what we learned about the sentence, right?
So no, I mean here in the box is well, in a way, I mean there's a dense sentence representation which you learn on one task, and this network basically it's about the network and the parameters. So this network can create a dense sentence representation, something like word embeddings for words, but embeddings for the whole sentence. So far so good. Okay. And then you just take the network, plug it here, and training on another task here, one task, and it'll give you some other sentence representation for this task But since it has been pre-trained to learn representations on other tasks, you learn better representation, which is more generalizable. Does it answer your question? Okay, cool. So the thing with RNN is that if you remember that, it was a sequence of tokens, and we had these transitions from, using the state vector or memory vector from one state to another, and consuming input. And as you might see, well, this is sequential, like inherently sequential in nature, right? You have to consume one token, do the computations in the LSTM cell, go to the next token, do the computation, next token. So you always have to wait, or it's like sequential. You have to wait for each things to be computed, which is nice and it works, but you cannot really parallelize these computations. You cannot just take each input token independently and do the computations, because you're always depending on the previous state. So that's a bottleneck of, not theoretically of RNN, but basically practically, because you have to wait. And if you cannot parallelize, you might be getting into troubles because things take time. So, but when the goal is to learn good representation of the input sequence, so this is the goal. We want to learn representation. So the goal is to learn good representation of the sentence. We might have better or faster architectures. And so RNN is great. It learns a representation of a sentence. It could be used, like here, for learning representation which can be transferred to other tasks, and it will give you gain. But it's slow. Also, what we're going to solve today is not only how to make this fast, or which architecture could be faster than just RNN and waiting for each input, but the static word embeddings, they have some disadvantages. And what is the disadvantage of static word embedding? So static word embedding is a vector representation of a word. But what are the disadvantages of static word embeddings? You remember one. One is it's great. You have embeddings for each word, but why is it? Exactly, it's without context. There is no context to plug in. If you have words which have different, I think it's called polysemy, if I'm not, multiple meanings for a word, then it will always have the same embedding, independent of the context. Even like from the context, it's clear. I sit on the bank. Then the bank is not like financial institution, it's a thing where you sit on, so it should have different embeddings, because embeddings should incorporate the meaning of the word, than, I went to the bank. But the bank will always have the same, so this is like embeddings without context. So what we really want to learn representation about the input is something which is fast, and something which is contextual dependent. And this is what we're going to tackle today. So welcome to BERT, B-R-T architecture, which is bidirectional encoder representation from transformers. It's been here since 2018, I guess. 2019 is the paper published. It won the Best Paper Award at the NLP conference. And maybe it's now a little bit out of fashion because we have other architectures like a GPT, but this is very important building block, like a game changer basically in the whole field of NLP. So one of the game changers was word embeddings, and the other is the BERT model. And why is it so? I mean, I just looked into the abstract yesterday again, and there's like, BERT is conceptually simple and empirically powerful, but it obtains new state-of-the-art results on 11 natural language processing tasks. Like, you're really beating many things at once, including pushing the GELU score. So GELU score is some natural language understanding benchmark. By 7.7 absolute improvement points. Like, whoa, this is huge. At the same time, it's improving natural language inference accuracy by 5 absolute improvement points. Question answering by 1.5 points, and the question answering version 2 of 5 points. So, wow. I mean, this is just one architecture which you could train, and it beats. It makes like massive improvements on 11 data sets at once. This is like a game changer. And the reason why it works is, and actually like, well, how it works, you don't need like training data. You don't need more training data in terms for each of these tasks. You just need to pre-train the architecture in clever manner. I mean, there's the architecture and there's how you pre-train it. And then the rest is just multitask learning or transfer learning. You have something pre-trained and you apply it on these tasks and just go up. So that's the reason why we talk about BERT. Transformers originally was sort of proposed or invented in 2017 in the famous paper, Attention is All You Need. But we're not going to start with this paper. We're going to start with the BERT architecture because this is a part of the bigger transformer architecture. And we'll talk about the rest in the next lectures. So we'll start from the BERT. So BERT is an encoder architecture. So what is an encoder architecture? It's basically you take an input sequence and you learn its representation somehow. Could be a vector, could be a matrix. You learn a representation of a sequence. So it's called encoder. You encode a sequence of tokens into something which is which represents the sentence in a good way. So you can make classification on top of that or something else. So for instance, very abstract view on this is that you have your input text, so some lorem ipsum, which is consisting of tokens. So tokens could be words or subword units. We'll get to that later. Then there is something which I just depicted BERT, well, some architecture, some neural network. And what's coming out is that it learns basically, it actually producing word embeddings. So for each token, it's producing a word embedding, but these word embeddings are contextualized, which means these word embeddings actually take into content the context. So for example, if I had I was sitting on a bank and I went to the bank, the word bank in these two sentences, after being pushed through the BERT model, would have different embeddings. So the context will be in there, which means it will work better for most of the tasks because I can represent words better. That's the idea. Basically, BERT is take the input and give me a bunch of word embeddings for the tokens, and these word embeddings are better than static word embeddings. That's the main idea. That's maybe what you should remember about BERT. And then what can I do with these word embeddings? Well, I have some tasks to do like sentiment classification or others. Yes?
What structure do these conceptual representation tokens have? So is it the vector? So
this is a vector.
Okay.
So it's a bunch of vectors, the same as standard word embeddings.
So basically we input a matrix and output a matrix. I mean,
we input a sequence of tokens and get a matrix out of it.
Okay.
Something like that. We'll go into very nitty-gritty details of that, but conceptually, these are vectors. Okay, any other question? So this is very high level. The question is like, what is in the BERT? Like, why does it work and what, how can we train it? But BERT produces contextualized word embeddings. And the idea, BERT learns them in a very clever way. And it can be applied to many downstream tasks. The point is like here, we call it fine-tuning. So we take the pre-trained BERT and then fine-tuning for some other tasks. So plug it as a pre-trained model and put some other smaller model on top of BERT to learn the task. We are talking about 11 tasks. So, BERT can learn representations for 11 different tasks or any task if you want. So far, so good? Let's dig deeper. So, BERT is a neural network. A neural network is a computational graph. There are boxes which are connected and there are matrices going through the network in the so-called forward pass. And how I'm using still the same colors and the same depiction, like everything which is green are some functions that have trainable parameters. That's it. So there will be some weights, there will be maybe some matrices, and if it's green, it's you learn it by what? How do you learn the parameters? What's the only algorithm you need to know from deep learning? Yes, gradient descent, stochastic gradient descent, exactly. It's how you update them and how you get the gradient by doing backpropagation on this computational graph. These are two main building blocks. So here, what's coming in is input sequence, and then what's coming out is some matrix. Yeah, exactly. So, and here in between, these are just placeholders for some updated token embeddings. So as you see here, there is something called transformer encoder layer, and there's a couple of those, so L layers. And this is something you need to, if you design a network, you can decide like how many layers of transformers are you going to plug in. What is the main limiting factor here? How many layers to have in your network? What is the main limiting factor? I can have like 8, 16, 32, 128 layers. What is the decision factor? I mean, maybe I need more. The more, the better. But there's a limit. What is the limit? What do you think?
Probably like something about computational power.
Computational power. And exactly what is it? I mean, computational power will be a problem, but what exactly will be the problem? Any idea? Memory. Memory on GPU. You have GPU, it has memory. I don't know how much, like 16 gigs, 32. If you're lucky enough, you have 800 or H100, you have 80 gigs, and I think that's about it. Yeah, so everything has to fit into GPU. If it doesn't fit your GPU, you get like out of memory errors, and then you're doomed. Because this won't fly on CPU. Because there will be some very heavy matrix multiplications down the road, and it doesn't make sense to run it on CPU. On GPU, it's just like 100 times faster or 1,000 times, I don't know. So memory. But well, if you have if you're rich enough, you can have deeper models. So this is one of the factors. But basically, these are repeated. So we should look into the transformer encoder layer because they will be repeated. So this we should explore in detail. And so some notations here. I'm gonna use, so for a set of integers, I'm gonna use just this these brackets and saying n, so this is 1 to n. For example, t is, in this means like t is iterating from 1 to n. So just simplify the notations here in the algorithms to make it shorter. And what I'm actually be using here in this lecture is a very nice paper from Pong and Hutte, formal algorithms from transformers. I think these are from DeepL, or Google Brain DeepL, I guess. And I recommend just to look up the paper if you don't know. The only difference between our lecture and the paper is that they use column vector notation, and we decided in the lectures a vector for us is a bunch of numbers. It's a row vector. So here in the lecture, everything is row vectors, and in this paper they use column vectors. So just make sure like things are transposed or not. Okay. So the BERT is basically a function. We can call it encoder transformer, and the input is x, and there are some parameters. So what is the input? The input is a sequence of token IDs. So far, so good, right? I mean, what is a token ID? We have vocabulary. Each word, or vocabulary, we have a vocabulary of tokens. Could be subword units, sentence piece, word piece, everything we talked about already. So the sequence is token IDs. And the output is typically an embedding vector for each input token, or it could be a matrix we can project some embedding vector back to the vocabulary by projecting, basically by having each row of the size of the vocabulary and having a distribution out of it. So basically having a distribution over different words. We will come to that later. So for now, it's just, let's take embedding vector is, so the output for each token is just an embedding vector. So for example, the input sentence could be the cat set, and these are the indices in our vocabulary, in our token vocabulary. So this is the input sequence, and I'm transforming this into the first layer, or the first thing I'm going to do is to transform the input of IDs into input embeddings. So I need to embed these discrete tokens into some embeddings. And what I'm doing is basically just the same thing we did with training word2vec. So I have some projection into some latent space of the embedding. So the embeddings I mentioned is something I decide, and I just project it to this matrix. So basically, this length corresponds to number of rows here. Like each input has a corresponding embedding. And this will be through the whole network. Like at the end of the network, I will have the number of embeddings corresponding to the number of inputs. So input embeddings. Any question? I mean, I'll train it. Obviously, this is trainable. So these will be trainable parameters as we had in Word2Vec or other embeddings. So I will train how to map ID into some latent representation. So far so good? So we have input embeddings. Well, input embeddings is just not enough. Not enough. And there's reasons for that. We're not going to go into the details, into the history of that, or the mathematical reasons, but we need something more than just input embeddings. We also need something called positional embeddings. So we also need, the reason for that is if you want that all these operations in transformer are translation invariant. So basically, it wouldn't matter if you move the token from one place to another. So we need to know like where these tokens are. Okay, so there's a reason. For each input position t, so for each token 1, 2, 3, 4, 5, and so on, we also learn an embedding for a position embedding for its position. So basically, we're saying token at position 1. No matter what the token is, but at position 1, it will also have some embedding. We'll embed position 1 into a latent representation. So basically here, the matrix would be for position 1 until L, which is the length of the sequence. We also map it to each position will have some vector of a dimensionality we can decide. And this is again trainable. Well, it could be trainable, or it could be, or just a function. In the BERT model, they use some cosinus, sinus thing. So if you look up BERT on like BERT tutorials on the internet, you will see like, oh, position embeddings are cosinus and sinus. It's possible, or it could be trained. The main idea is that for each word, we have two things. We have the input embedding, so it maps input sequence to something which is related to the word. And then it maps it to something which is related just to the position. So each position has also an input embedding. Yes?
Things like subjects also in the first position probably, so has a different meaning than the word that's in the back set.
Well, yes and no. I mean, yes, you will need to know, like for each of the words, you also need to know its relative position or its absolute position. So that's why it's important. And if you wouldn't plug the position embeddings, all the further transformations in the BERT model wouldn't be able to pick up where the word is, because they will be just multiplying matrices, and if you multiply matrices, the ordering of the rows doesn't matter. So it wouldn't learn any positional stuff. So that's why you need to plug it in the first place.
The word embedding, is the first output vector related to the first word, or is it?
Yes. No, I mean, so the word embedding, so here the word embedding is just the word embedding of word ID 21. So for example, the has an input word embedding, and it will be all the same. Like for if here we had 21, so the embedding would be the same, because the ID is the same. But then we combine these two things together, and we'll have position embedding and word token embedding combined together, which will make it distinct. Does it make sense? Okay. So the thing is, I mean, positional embeddings were proposed for, we didn't talk about it, for convolutional neural networks, which is a thing still in computer vision, in NLP, not anymore. But they were introduced there for the same reason as we just discussed, and they use it for machine translation and get state-of-the-art results, which are 10 to 20 times faster than LSTM. Because you can parallelize these, if you're using convolutional neural networks, you can parallelize, and if you can parallelize, you can train longer, and then you just get better results. Basically, that's it. So that's what you want to really parallelize, and it's a bottleneck of, for example, LSTM or RNN. So that's where the positional embeddings were proposed for the first time, as far as I'm concerned. Okay, so here, just explain. So we are continuing the algorithm. So the length L is the number of tokens. Okay, so far so good. So for each token here, we're getting the token embeddings. So this is a lookup operation in the embeddings matrix, and we're summing it together with the positional embeddings. And again, this is just a lookup. So we are looking up the row of position T here, and here we're looking up the row of the token ID. So this is just to explain like what we're doing, like in sort of like algorithmic way or mathematical kind of expression. So we're summing them together. We're taking the token embedding and position embedding and just sum them together. which means for each token, then we have like, for each token we have unique representation, so to say, because the word bank at position 1 will be then different from bank at position 5 because of the positional embeddings. And then what we're gonna do, we just stack them row-wise. So if we have these vectors, E, so we have the cat set, and each of them has a vector E1, E2, and E3, what we're gonna do, stacking row-wise means we just create a matrix out of it. So this will be a matrix of, so this is a vector, this is a vector, and this is a vector, and we just turn it into a matrix, but it's just a bunch of vectors in a way. Okay, any questions? So far so good. So we're building the transformer from the bottom. Okay, so we turn the input tokens into embeddings. This is good, and then, so we are here, these were IDs, we turn it into embedding matrix. Okay, good. And then, as I said, like the transformer encoder now, it's repeated L times. The only difference is, I mean, that's what I said, like, you know, you're running out of memory means that each of these layers has some parameters, and these are different for each layer, right? So that's why you need, like, if you add another layer, you will need to store the new amount of parameters on your GPU and your RAM. That's the reason. So let's have a look into this. So just adding to our algorithm, okay, so this is what we had so far. And then we'll just repeat for layers from 1 to L. Okay, right, this is basically repeating like 1 to L. We're gonna do something. So what are we gonna do? Let's have a look into this single transformer encoder layer in detail. Okay, so this is how it looks. Don't be scared. I mean, it's like, what's going on here? But we'll discuss it. I mean, no worries. What we can see here, I mean, the input again is, what was the X? It's a matrix of, this is L, number of tokens, and this is some dimensionality which we decided. So this is what's coming in. And it's flowing through a couple of operations. Some of them are trainable, like the green ones, and some of them are just functions. So sum is basically not trainable. So it's summing up something, then passing to some other function, then passing to summing, and so on. But eventually, we end up with, again, with a matrix of size L, and most likely the same dimensionality. This is what we want, because we want to repeat this again, like not recursively, but just another layer with the same kind of structure. Okay, so it means there's a coming matrix. The matrix is, for each row, it's a embedding for the token. We're gonna do a few operations and end up with matrix of the same size, where the embeddings are somehow updated. Why they are updated? What does it mean to update? Well, because as you might see, here, the vector basically goes through some operations like directly. So, and there's always some extra path, and there's something updated here and added, and here there's something updated and just summed up, and maybe there's discrete operations in between. But basically, we are somehow still updating the original thing and adding more stuff to that through these extra paths. Okay, so on the abstract level, any questions? Does it make sense? Good. So there's a thing called multi-health self-attention. Whoa, okay. So what the heck is that? So matrix coming in, matrix coming out. Okay, cool. So let's have a look. But before doing so, let's just add this first the first part of the multi-head attention, the encoder layer into the algorithm. So we're gonna take the X and sum up with a thing called multi-head attention. So this is the first part, right? I mean, we take the original multi-head attention and sum up with the original. So this is exactly explaining this part. And basically, taking the input plus something else, it's called residual connections. Residual connections. And these will be, as we saw, like residual connections are here. And these are some sort of like a highway of passing the information through the network without going through all these other transformation, because sometimes they're not necessary in a way. Why exactly it works, I don't know. So I don't think anybody knows, but this is how it works. Okay. So we won't learn today why it works. We will learn how it works. And this is again, like the whole thing about deep learning and NLP, like we know how. Why is much tougher questions. And this is something for research in theory of learning or statistical learning theory or machine learning theory. There might be people who know, but we know how. So, multi-attention. Okay, so multi-attention, let's have a look. Why is it called multi-attention? Because there are multiple so-called heads. This is it. So this is the matrix coming in. For each row, it's a vector, it's embedding vector for each token. And we have multiple of these heads. So we have age heads. So there is 1, 2, 3 until age. Again, how many heads can you have? 8, 16, 24. Say again, number of words? No, you can have any number of heads. So age could be something between 1 and infinite. Well, not infinity, but you could be infinite. Just these are parallel. So basically, what does it mean? You have parallel computations, and each of them have different parameters, different params. So basically, you're doing some sort of same operation, but every time with different parameters. Why? Why the heck? Why would you do the same operation like with different parameters? Any idea? Yeah. So for different things, I mean, there's no majority vote. You're just gonna stack them together afterwards. So the idea is that, of course, these parameters in each of these heads are, how do you initialize the parameters of your network? Randomly, exactly. So what happens if you initialize age heads randomly? What are you gonna end up with? With different random weights. Okay, so then you have different random weights, which means different starting points of your optimization. So what are you going to end up with after training the network? Do you going to end up with the same weights or different weights? Yeah, because most likely, because you started in each of these parameters, you started with different starting positions in your parameter space. And if you do like the loss optimization and things like, the loss and optimization and changing the parameters, most likely you will end up with different parameters after training, which means all these functions here, these are basically functions, all these will be different. So we'll end up with different functions working with the same input. What these functions are doing, well, who knows? But they're doing something interesting empirically, and there are many of them, so they are doing many interesting things at the same time, and you just cram them together. That's the reason. What's preventing you of having infinity heads at the same time is your memory again. So you have to have, it has to fit your GPU still. Like it's gonna be a huge model, so it has to fit. So attention heads in the original BERT, how many? 24, 12, maybe 12 heads, maybe 12 heads. It's growing. I mean, the bigger the GPU, the more heads you can have. But you have like in parallel also the many heads. They have the same functionality, but they will learn different functions because they are trained different. I mean, they're initialized differently.
The accuracy of the model improved with more heads.
So in general, the more the merrier.
Yeah, but like how, like quantitatively?
Yeah. So I mean, general, it's hard to answer. So we'll be talking about large language models maybe in 2 lectures, and with some numbers like if you scale up the model, what's going to be the consequences, and the consequences are gains basically. How much depending on the task, how much data, how long you train and stuff like that. But there is improvement. Like the more, this is it. I mean, you just the only thing you need is hardware. Like these days, you just need hardware and transformer model and enough data. If you have this, everything else is just, you don't need anything else, most likely. Yes? Mm-hmm. No, okay, we didn't. We have to go deeper. Sorry, yeah. I mean, attention heads. So we have so few of them, but we don't know what they're doing yet. We have to, yeah. So we have to, we have to ask her a question like, what is the attentional head doing? We're going to address this in detail, but there are multiple of them. Okay. So some notation details. We can concatenate matrices of the same dimension along rows. Means if we have, this is just, I just want to like really spell it because we'll be using this notation later on the algorithm. So if we have H matrices, and of course now we know the H is number of heads, so we will stack them basically one after each other. So basically concatenate these matrices along the rows to get this large matrix. We can stack them like along the rows, or we can stack them along the columns. And here I think they were stacking all the columns. Actually, at the end of the day, I don't think it makes any difference because there will be some multiplication again, but doesn't matter. So this is just stacking matrices. Okay. So now we need to describe this thing, multi-head self-attention, which is, so okay, the input is the matrix. So number of inputs times some dimensionality. So it's a vector representation of the sequence of length L. And output will be something of a different dimensionality. It's updated vector representation of tokens in the X. There are a number of attention heads. We just discussed this already. And then there are parameters for each head. So, and we said already for each head, the parameters are different. Like different initialization for each head. And it will end up then trained differently. So we can ignore this. I just, for your reference that, at the end of the day, there are some matrices which have dimensions and they have to match. So, but the function is simply for each head, just compute the attention. We don't know what attention is, but we'll talk about it later. So for each of those things, we have the attention head. What you see here, and then we stack these together and then do some linear projection. Okay, so we didn't talk about it, but this is basically it, stacking them together and do some linear projection to some other thing. So what is linear projection? Multiplying thing by a matrix. It's linear projection. So what do you see here? This is interesting. What is nice about this thing from a computational perspective? It can be parallelized. Why? Because the inputs are given, so you don't touch it. There's no dependence on the input, like it's given, and there's no dependence between the attention heads. Each of the head has different parameters, so you compute them in parallel. Awesome, exactly. That's why it's awesome, because you can parallelize so many heads in parallel on GPU, and GPU is awesome in parallelization. Okay. So you don't have to wait for one head to finish before you do another head. These are just in parallel. Okay, so it didn't answer the question what is attention, so we're gonna go to it, but there's multiple heads. So what is the attention basically doing? So this is a single attention head. And again, it looks complicated, but it's not at the end of the day. So we're gonna go through this. So again, the input is coming in. So again, what was this X? What is it, the matrix? How many rows do we have in the matrix? We have number of tokens. Number of input tokens is the size of the matrix. What is the number of columns in the matrix? Who knows? Some parameter. We just decide like 500 something maybe, or 1,000, or I don't know. This is a parameter we decide, like hyperparameter. Okay, so this is a matrix coming in. And then we're gonna do three things. We're gonna put it through so-called the query layer. So there's some linear layer, and again, green boxes means parameters, like parameters, which means you can train this. So there's some parameters for linear layer. So linear layer is just projection, right? I mean, linear layer, you just take a vector, project it through the matrix to another vector. This is linear projection. Now we're multiplying bunch of vectors by a matrix. Give you a bunch of vectors. It looks like multiplying two matrices, but what you're doing, we're taking a vector for a first row, multiplying by a matrix, get us vector for a first row again. Second row, multiply by matrix, project it to another vector. right? This is why it's matrix by matrix multiplication has different meanings. In linear algebra, matrix by matrix multiplication is like two linear maps together, something like that. We're not doing this. There is just you take a vector, multiply by matrix, which means you project it to some other space, and you get another vector. If you have multiple vectors on the input, you will have the same number of vectors on the output. That's the main idea. But if you cast it at multiplying two matrices, we have algorithms which are super fast for multiplying matrices. That's the advantage. Does it make sense? Multiplying vectors by matrices? You should know it already. If you don't really try, really brush up your linear algebra thing. Okay, so we have the linear layer here, which is, we have the query. So we project it to something called query. We make some linear projection to the key, and we make some projection to value. Why? We'll see later. Which gives us three matrices, Q for query, key for K, and V for value. Then we're gonna do some these are the only parameters we're gonna train. Then there is some operation called scale.product. Okay, no idea what it means, but we'll figure out. It will give us another matrix. Then there is some softmax over rows. I think we can figure out what it means, but we'll talk about it later as well. And then after these fancy things, which has a meaning, as we will see later, then we just take the value and multiply it by this input to get the output of the head. Okay, why? So let's have a look in the detail. So here's a very simplified example. So we have a couple of input tokens, the cat set, dot, and some padding, and they are corresponding to, there are some embeddings here. This could be the input embeddings, or this could be embeddings from the previous layer, doesn't matter. So the embeddings, now we say we project the embeddings, project to the query matrix. So this is the query matrix, and the dimensionally could be different than these embeddings. But what is important is that each of the row corresponds to one input token. So this is important, right? Because still we are working on the token. Each token has its embeddings, and we can project them into some other space, but the number will be the same. So now we have 5 times something query matrix Q. And as we saw here, we're gonna also project the X into the key into the key, again by linear projection. So we projected X to a matrix key and then transposed. So we're transposing this. Did we have it here? No, we didn't. So we're transposing the K matrix. So, and then we're gonna multiply these two matrices together, right? We transpose it, which means this is the length of the input, L, which is 5. And then what we're gonna do is to multiply these matrices. Well, what does it mean if you multiply these matrices? So how do we multiply matrices? We take the first vector here and the first vector here, and we say the first item times first plus the second item times second plus, which will give us the first entry here. What are we actually doing here? Yes, you have a question? No, we're not squaring nothing yet. No, nothing yet. We just multiply. We just have two matrices. Each of them is a projection of the input to some other space through learned parameters. They have the same, they're matching their dimensions. What we are doing if we are multiplying these two vectors like that, what is it? It's a dot product. It's a dot product. It's a dot product. If you take this vector and multiply by this vector to get this number, it's a dot product. You take the first item times the first, plus second times second, plus third times third. We're doing dot product. What is dot product? We discussed dot product in detail. What is dot product saying?
Similarity of vectors.
It's something about a similarity of the vectors or some strength of association, right? So basically, this output is telling me the strength of association of this row, of this column with the first of the, of the representation of the first token in the key and the representation of the first token in the query. So they're telling me something about how these two tokens, after projections through query and key, are, well, similar in a way. Like dot product is something about similarity. I mean, there are some nitty-gritty details about it, but it tells some sort of like strength of association. And which means then I'm gonna take the first word, the first token, and then do the dot product with the second token to get the second value. Then again, the first token with the third token to get a third value. And I'm gonna repeat this for second one with the first one to get this. So basically what I'm creating here is some sort of like associations between each word with each word. So each word now knows, in a way, or should learn. Why learn? Because we're projecting this. There will be some ways how to project it, right? But after the projection, words that are important to other words should know about it. And how? Well, because we're looking at their raw association. I mean, their association through the product. So it has something to do with like importance or not similarity of the embedding. So we're in the embedding space. This is kind of tricky, but there's something about the you know, how close to each other they should be in this embedding space. So there should be some sort of information here. And there's one little detail. So we just divide each entry by the dimensionality, by some number, by some constant. So square root of the attention, of the dimension of the attention. Why? For numerical reasons, as far as I remember. So we just divide each number by some constant. But roughly, we have these raw associations. So far, so good. These are Q and K are learned representation, which means there's some matrix for projecting into Q and K. But afterwards, we're taking the product of each word with each word. Which means we're also looking, if we take the last word and want to see some association with the first word, we're looking to the past. And from the first word, we're also looking to the future. So we're learning the representation of the input sentence, of the full, but also there is no left to right. That's why it's called bidirectional encoder, because we can loop into the future. Like each token knows everything about the future tokens and vice versa. So you can look at the whole sentence. This is one feature of this encoder. In the decoder part later on, it will be different. But now we can take the whole sentence. So once we learn this, we're going to turn it into something more important. But so far so good? Okay. Here we have, again, we have this matrix, which is now 5 times 5 of these raw associations. And, you know, it's still, there is some correspondence. Like these words still somehow correspond to the position of these input tokens, right? This is still, they have some relevance because how they were created, like from the query, right? So there is still the number of these rows is corresponding to the number of input tokens. What we're gonna do now is to turn this number. So these numbers could be, what is dot product? Could be what? Could be, is there range for a dot product? Could be. Say again?
What is the input range?
No, the output, the range of dot product.
Depends on the input.
Yeah. So is there any range?
Yeah. I guess.
Could be any number. Dot product could be any number,
yeah.
Like minus infinity plus infinity. That's the point. So we want to turn it into something very nice. We want to turn these numbers, which could be, so each of them could be in minus. Could be any real number. We want to turn it into a probability distribution. So each row should sum up to 1. How do you turn, no, I mean, you have the answer, but why? I mean, how do you turn a bunch of numbers, a vector of numbers, which could be anything from minus infinity plus infinity, into a probability distribution? Softmax. Softmax? Does it ring a bell? It should. Softmax is exponential, like for the properties, it's basically turning everything into a probability distribution, which means all these numbers will be somehow between 0 and 1, and they will sum up to 1. That's what Softmax is doing. Okay? Cool. So now we turn this into Softmax. Okay, so it's giving me, what is it giving me, by the way? Something interesting. It's giving me normalized associations. It's giving me some weight. It's giving me, so for the first row, for example, here, this is giving me some sort of alpha or weight or alpha. How the second word is somehow important for the first word. Here, this is how the third word is important for the first word, for the first row, and so on. And here, for example, this would be like how the first word is important for the last word. But now these things are probabilistic, so everything will sum up to 1. Okay, yes?
The matrix is not symmetric, right?
It's not symmetric. No, it's not symmetric.
Because so one word could be important for another word.
Yes, but not vice versa.
Probably important for the noun, but not necessarily not.
Exactly, yeah. Okay. This is not symmetric for a reason, like, because these are, I mean, the key, it will be only symmetric if Q and K were the same matrices. But these are not. There are two different projections. So that's, you have two matrices, multiply them together, so the result is whatever. The meaning is, though, the importance for the other word for the current row. You had a question?
The first question is, how can you tell the second word is very relevant to the first word? Is it because, let's say the first one is 0.1, so the second one is 0.3, or the third one is 0.5?
Yeah, so how do you tell? Okay, how do you tell, what does it mean, like the word is important? It means the alpha, the weight, will be higher. So for example, here, this is a small, the alpha will be small, and here, this will be higher. So the higher the weight here on the word, the more important it is. So the more attention should the other word pay to this word. Well, the order is here. I mean, the order is still, the order of words is here. So the ordering of the words is reflected in this indices of the matrix, in the row. So each row of the matrix has is corresponding to one input token. And then after this multiplication, each column also corresponds to token in the input sentence. So you know exactly what is it corresponding to.
And also, can we just keep all of the layers to do the softmax first?
Well, why? No. I mean, you could, I think. So
the purpose is to find how relevant the neighbor word to find the meaning. I mean, to turn the random path into something meaningful, right?
Well, okay. So I think you're asking. So this is like questions of very many levels. So how do you tell? How do you know something is meaningful to something else? It has the network has to learn it, and it has to learn it through. So there will be some loss somewhere down the road. We don't know yet what the loss will be about. We don't know the training procedure of this model yet. But yeah, it's random. Like of course. And then through updating the parameters, it will learn how to perform the task better, whatever the task is. So it will learn these projections so that will be meaningful. So these projections should learn automatically for which word I should pay attention to which word, and vice versa. It will learn these weights automatically, basically, through the matrices for projecting Q and K. Sounds like magic to me. Yes, kind of. Yeah. But then, if you really, so you can really then look, this you can visualize. For each attention head, you can really visualize these associations, and it will tell you which word is relevant for which word at which kind of part of the network, and you will see something interesting, like, oh yeah, maybe it's paying attention to syntactic, like syntax, for example, like the same. Okay, do we have the linguist in the room? No, we don't. Okay, so there, long-range dependency. So you'll see dependency between two words will be highlighted by high attention values here. Like these words should attend to the other words, and the network has learned this. And you can visualize it by showing this histogram, basically. Because I mean, eventually here you get a histogram for each row, which you can visualize. If you have 12 heads times 24, you can visualize this thing and then have a look like, oh, in which head, which word is important for which other word. And sometimes it makes sense. Most of the time it makes sense. It's really learning like the dependencies between words. And you can just, look at the attentions and click on that. There's tools actually, trying to visualize internals of the transformer model by showing the attention, like which word is important for which word. Cool. So we have these weights. What are we going to do with that? Eventually, so again, here, this is, for each row, this is some sort of like histogram summing up to 1. So we're going to take this. And remember, we had query key and value. So far we discussed this projection, then scale.product, softmax per row. So now what is coming here is a matrix of probability distributions for each word with respect to another. And then we're gonna weight, basically using these attention values, we're gonna weight the value matrix. So the value matrix is another projection of the input. Again, this will be size of length. This will be some other dimension. And since this is again 5 times 5, so the length, we're gonna multiply this. And what is it saying now? Okay, so for each, I'm taking multiplication here. So I take the first row, which is a string of association between let me tell it differently. Like, to which words the first word should pay attention to, and it's going to be multiplied by the first column to end up with the first value. So it's basically saying, what is it saying? It's basically weighting each vector. Oh, okay, by the way, yeah, in a way, this is the first value, then it's take the second value, the third value. Oh, we are basically weighting the other vectors and sum them up, right? I mean, if this is like 0.1, then after this multiplication, I'm taking 0.1 times the first vector, then maybe this is 0.2 times the second vector, and then the other numbers times the third vector, fourth and fifth, sum these weighted things up, and end up with the first vector. Does it make sense? Like, this is basically, this multiplication is under the hood, is weighting the other vectors, like weighting these. So this is, if this were, for example, if this were 0, 0, 0, 1, 0, which means for the first token, the only important part is the fourth token. This is like the strongest attention. Everything is 0. It will never be like that because a 0 is impossible after softmax. But let's say it's like that. Then the resulting row here would be what? So if you take this vector and multiply, do the matrix multiplication, you will basically end up with just the fourth vector, the v4. Right? So, okay, now let's say it's 0.5 and 0.5. What you end up with now in the output vector? Half v3 plus half v4. And so on. So if this is like a general probability distribution, then you are basically weighting the other vectors. So this attention learn to which other words are important, and then by these importance, summing up or making a weighted average of all the other word representations for its output. So not every matrix by matrix multiplication is just a linear projection or matrix multiplication. I mean, they have different kind of maybe meanings, like, at least as I understand them. Here, these were dot products, some raw associations. Like how much is this word should be associated with this word and with this word and so on. So these were associations. Represented as matrix multiplication, of course. You can just multiply two matrices. Here, the matrix multiplication is basically weighting the other tokens to create a final token representation. And the weighting is determined by the attentions, like to which words I should pay attention to. Okay? So this is my summary of this thing. Any questions? Okay, so I would say like give it some thoughts, go through slowly and just try to kind of do it per hand and you will understand what it means. That's the best way, I guess. Okay, so this was the self-attention detail, right? I mean, this is what we had. So matrix in, Q, K, and V, scale.product, the associations, and then getting the output as a vector for each, as a matrix of updated representations of words from each head. This is what you're getting. We discuss the details. And then, what are we going to do with that? Okay, some notation details. How to add single vector B to each row in a matrix. Okay, so this is not important for now. I mean, this is important for the algorithm on the next page, but it's basically, you can look it up afterwards if you want. And also, like, how to do softmax for row-wise. Okay, I mean, because softmax works on a vector, so if you want to do it row-wise, you just apply it for each vector. I just want to spell it out like very precisely, so if you really want to implement it, you know like how to implement it correctly. Okay, but in just, if I say softmax over rows, this is how it could be like, in detail. So here's again the same, so I mean this depiction here as a graphic depiction is here again as an algorithm depiction. And what we see here, so the attention, again, the matrix of embeddings is coming in. And then we do 3 projections as we had. So we project to the query, which is matrix multiplication plus bias. We project to the key matrix, which is matrix multiplication plus bias. And we project to the value, which is matrix multiplication and bias. 3 linear projections. Then here we do the raw association, so basically the 5 times 5 matrix we had in the example, and divided by some normalization constant, so this is the scale score. And then we row the softmax on each row and multiply by the value matrix to get the output. Like this is the same, just in an algorithmic way. If you wanna implement it, this is how you basically write it, sort of. Okay, so this was the one attention head. A long way to go. It's a complex model. So again, we're zooming out. Remember, we were here. Then we said, let's look into the encoder layer, transformer encoder. So the transformer encoder started with the multi-head self-attention. Then the multi-head self-attention have multiple heads. Each of them have different parameters. And then each head is consisting of this query key and value magic here, sort of, doing this thing. So now we're zooming out again. Okay, so we had this. So far, so good. We talk about the residual connections in the sum here. So we sum up, we did some updated representation. Here, this thing learned something about the other words already because of the self-attention, because of attending to the other words. So it updated the matrix in some contextual information. And we just say, well, let's keep the original as well. Just don't throw it away, just keep it and just sum it up together. Because why not? Maybe what's learned here is not really important and maybe just the original is so important. So then there's 2 things going on. So there's something called layer normalization and there's something even worse. Well, not really. Okay, so let's look at layer normalization and this thing called GELU. Before doing so, let me just replace this with ReLU. Okay, so what is this thing? We have linear projection, some nonlinearity, and some linear projection. What is it? Does it have a name? It's a neural network in a way, like a small tiny block of neural network. Linear projection, nonlinearity, linear projection, maybe some nonlinearity. Do you know it?
We use that for classification, right?
Yeah, in a way. So what is it? It's a neural network. Okay, so multi-layer perceptron or feed-forward network. Feed-forward. Plain and simple feed-forward net. Take the input, multiply by matrix, project some to some other space, do some nonlinearity, ReLU, GELU, whatever, then do the projection again, and then you have some better representation. So multi-layer perceptron or feed-forward network, like basic building block of neural networks. Okay, so now we know what is this doing. So it's basically taking the input and projecting to something else, whatever it is, something interesting. And then we need to only understand what the GELU thing was and what is the layer norm. And then the rest is basically, the rest is done. Okay, so let's have a look what is layer normalization. Any questions? Like feed-forward network should be your friend. I mean, NLP, you should know this. Okay, so layer normalization. It's a very fancy algorithm for something which is super. So let me just explain it with words first, and then we can look at the notation. So words. Vector is a bunch of numbers. So what you want to have is that the bunch of numbers is centered around, maybe around 0. Right? So you shift all the numbers that are around 0, which means the mean of all the numbers will be 0-centered. And then you want to maybe scale it that the standard deviation of these numbers is also maybe 1. So this is it. You have a bunch of numbers around the place. You want to shift all the numbers that they are centered around 0 or some other number. And you want to scale them up or scale them down so the deviation from the mean is somehow bounded. That's how you normalize it. Any questions? Like theoretically, no, like practically, what is it doing? Make sense? Like my hand waving here? Okay. Because you can do it very precisely in mathematical terms if you really want. So it's a bunch of, so E is a vector, bunch of numbers. You go through this bunch of numbers and take the sample mean, sample mean. So the average, you take the average number, and then you compute the variance, which these formula you should be familiar with from high school statistics. How you compute the mean and variance from a bunch of numbers. So this is it. And then what you're going to do is that, of course, for each number, you subtract the mean and divide by the square root of variance, which is the standard deviation. And then you can have some parameters like multiply each number by some other number and have some offset if you really want. So first you want to make it sort of standard Gaussian. You take a 0 mean and 1 square root deviation, and then you can shift it again if you will and squeeze or stretch again. But you want to normalize it. And typically, beta is 0, so you don't shift it. You keep it at 0 mean, and I think gamma would be typically 1. So you just turn a bunch of numbers into a 0-centered standard Gaussian thing in a way. Does it make sense? Why is it good? Why should we do that? Any idea?
Go back to a fixed range value. So
we put it into fixed range in a way. Why should be it important? I guess the reason actually is like numerical stability. For one or the other reason. Because if you have numbers like all over the place, then maybe it's not important to have them all over the place. But what matters is the relations between these numbers. So I guess it was like empirically shown if you put layer normalization, it just worked better. And maybe there's some mathematics like deep behind why is it so for optimization. But you just make it nicer for numerical optimization maybe. So this is it, layer normalization for a bunch of vectors. Any questions? Sorry, a bunch of numbers in a vector. So how to do it for a bunch of vectors? If we have a matrix m times n, then you do vector layer normalization on the first vector independently of the other, independently of the third, and so basically you normalize each row in the matrix. So each of them will be zero-centered, one standard deviation distributed in a way, independently. Why is it interesting here? What's the good about this algorithm? Computational wise? It's a recurring theme. Yes, you know the answer. Again, you can parallelize this very easily because each of the rows is just independent. You run it in parallel and speed up. Okay, so now we understood here. So we have these are some numbers, and we just normalize each row here and get some other numbers. And this is the same operation here. So these layer normalization, it really varies from one architecture to another. So I think in the original BERT, the ordering of the layer normalization was maybe a little bit different than in the transformer and then in GPT, but there are some layer normalization, all over the place to make it more stable. Yes. Oh, that's a good question. The only parameters for a layer normalization. That's a good question. How do I learn? Do I learn the beta and gamma? I think these could be learnable. Yeah, you can learn them, of course, because eventually here, what you're having is this function. Can you differentiate it? Can you make a derivative with respect to beta and gamma? Can you make derivatives of this function with respect to gamma and beta? Yes. You can make, yes, of course. I mean, come on. Like, okay, E with respect to beta is 1. Because it's, like. So the same partial derivative of E with respect to gamma is this thing. So you can update these parameters and learn them. Sounds good. Everything is computational graph. As long as you can take derivatives, you can learn it. Yeah, good question. Exactly. That's why it's green. So we have those things. Now let's have a look at these fancy GELU thing. Okay, so is it any different from ReLU? Well, yes and no. So I'll just show you a picture and you will understand. So this is GELU. And how is ReLU looking? ReLU is just here, it's a line, and here there is some, in GELU there's this little, kind of tiny little, how do you call that? Spline thing. So it's smooth, it's smoother. And it has a very fancy mathematics, so you can take a standard normal distribution, so this is the phi function is the CDF of standard normal, and if you multiply this by and you can do some approximations and whatever. At the end of the day, you have something like ReLU. The reason why there is GELU and not ReLU is not known to me, and I think somebody just decided because it works better empirically. I think if you put in ReLU, it will be faster, maybe. This is not bad because this is sigmoid, so sigmoid is fast. The derivative will be fast. Okay, I guess it's okay. I mean, so GELU could be ReLU. This is the only difference. So you don't have to remember any of those. I mean, it doesn't matter. But like GELU is some sort of like, this curve. Okay? Okay, now, wow, so we have it. We have one transformer layer. So multi-head self-attention. Then we normalize it. Then one part of that goes through some projections, some nonlinearities in between and coming back. And again, it might be important or not, so we just sum it up together with the original residual connections. And then another layer normalization. This is one transformer block. Many parameters here. So many parameters in the multi-head self-attention. So we have heads. Each head has Q, query key, and value. Here, these linear layers are also need to be somehow big. There's more projection in each of the head and the multi-head self-attention. So there's a lot of parameters. So, but let me just put it together in the, so we are where we are before. So we go from one layer to another consequently. Okay, here we cannot parallelize, of course, because the one layer comes after the next layer. Like in deep learning, like layers, right? So you have to do it layer-wise. But again, this is the first multi-attention, then the layer norm, then this fancy multi-layer perceptron, which I just spell out as two linear projections with GELU in between, and the first last norm. This is it. Multiply by how much you can fit into your GPU, and you have a part of the transformer already. Yes?
How well does it work out when something like this on FPGA?
FPGA? I've never implemented anything on FPGA. So how does it work? What is FPGA good for?
It's basically you can write networks in Verilog, and then you can synthesize it, and it basically emulates an ASIC, so it ships very efficiently.
Okay.
Okay.
If you feel like you wanna try, just go for it. Absolutely, go for it. What I know, like GPUs are good for all these things because everything now here, I mean here everything is matrix multiplication at the end of the day. Even like the derivatives will be like matrix multiplication. And you have on what is on GPU, like you have the what is this, the CUDA core and the tensor core. So NVIDIA chips, they have like the tensor cores, and the tensor cores are faster matrix multipliers, like trillions of operations per second. That's what you want to do. That's what's good for, 10 years ago, if you buy a graphic card, you want to do like gaming. Now, if you buy a graphic card, you want to do deep learning. I don't know about other architectures. There's another architecture called TPU, Tensor Processor Unit, which was built by Google a couple of years back, maybe 6-7 years back. And you cannot buy it, but you can buy it on their cloud. So they're running in their infrastructure cloud TPU processing unit. I don't know any detail. I'm not a hardware guy, so I don't know, but it just should be should be faster for deep learning, fast enough, but it seems like it's still comparable to NVIDIA, like the beefy machines, like the beefy GPUs. FPGA, I have no idea if it would be helpful. I mean, eventually everything can be run on CPU if you really want, but the fast parallel SIMD, single instruction multiple data, exactly. That's what you want. I mean, you're multiplying matrices here, so it goes fast. Okay, sorry. I just watched yesterday like a YouTube video like on how GPU works, and then that's what I remember. Otherwise, I have no idea about hardware, but I just remember this. So I'm not a hardware guy. Eventually, it's maybe interesting to know how the hardware works if you want to make really speed up things. But we have the abstractions of somebody programmed CUDA, and that's good. Okay, so here we are, and the thing is like, what is the final layer doing? Okay, let's look at the final layers. So the final layer is some linear layer projection, some GELU, some layer normalization, and it gives us a matrix, which we can then so-called unembed back into the vocabulary. Because, for example, what we want to do maybe is to predict a word. Okay, can we do that? Of course we can do that. We can, if we have the cat set, and we have the embeddings after BERT, then we can turn this into, vectors of size of the vocabulary. And this could be something like probability distribution over vocabulary, so maybe 0.1, 0.01, and 0.8 at some position, which means we can basically take or generate the word from this probability distribution by taking the maximum value. I mean, something which we did last week, did we? No, we took we are sampling from a probability distribution, so you can sample from probability distribution to turn this vector into word, which will be important later on for the learning of this network, and also for the transformer which generate text for the decoder only, GPT stuff. So, but basically we can turn this vector into a matrix of size, number of input tokens, and the size of vocabulary, and this can be very useful. So softmax over rows. That's how you turn it into probability distribution. This is our matrix P. So just plugging everything into this big thing, encoder only transformer forward pass. Wow. So if I just show you this from the beginning, you would just leave. But now we went really through every nitty-gritty detail of this thing, So you should be able now to actually implement it. Like if you know PyTorch good enough, that should be possible to build. Because at the end of the day, what you need: matrix multiplication, matrix indexing. You can slice tensors, right? You can slice in NumPy. So matrix indexing, matrix multiplication. There was one transpose operation. I think you can call torch.transpose to get transpose matrix, as far as I understood. We have softmax implemented in PyTorch already. Okay, GELU. You can close your eyes and just use ReLU, or just you can implement ReLU. You can implement GELU if you really want, but you can just implement ReLU. It's the same thing almost. And layer normalization. Okay, but I guess like everything is already in PyTorch, like as you know, in the standard library. So that should be it. You should basically be able to stick everything into this, like 20 lines of code, using PyTorch things, and being able to build this forward pass. And the thing is, if you do it in PyTorch, that's only what you need, because PyTorch already does the backpropagation for you in a way. Like all the operations, they already know how to do the derivatives and how to stitch it together to the computational graph and how to train this. So this is basically all you need to implement. If you want to really implement it from scratch, like from zero, you would need to, for each of the operations, we would need to know like how to do the derivatives. But that's what we know already. I mean, we now learn how to do derivatives for the layer normalization, for example, and it's easy. So all the other operations are the same. Okay. So this is the forward pass in BERT. This is just a reference, like all the parameters, hyperparameters. There's lots of parameters for BERT. These are basically weights of the matrices. Okay, so the layer normalization parameters are here. Another matrices and biases, matrices. Lots of matrices, lots of parameters will be learned. You initialize them randomly and then you learn them. And I think we should maybe today stop here and take the second part of this lecture next week to discuss how the hell do we pre-train this thing or train this thing to do something meaningful. Okay, thanks a lot.